So welcome to Lecture 17 of my General Relativity course. Um, Today we're covering essentially Chapter 5 of Sean Carroll's book, which is on the Schwarzschild solution. Schwarzschild was an interesting character. He did work before this, notably some things with writing down the right Lagrangian for electromagnetism. And I'm trying to remember, I don't remember what else. I was looking at his Wikipedia article earlier today. It's interesting. So sadly he died a year after he published this. So he published this within like a month of when Einstein published General Relativity, and Einstein approved of his work and publicized it. So that was kind of neat. But anyway, so he died. I think he did this work possibly in the on the battlefield in World War I, no less. And I guess he died from a sickness about a year into that, in I think 1916. But in any event, his work lives on here, so let's look at it. So the Schwarzschild solution is it's basically the spherically symmetric solution to Einstein's equations. All right, so vacuum solutions. So in the sense that you have, basically you're thinking of there being a point mass at the origin of this space, and the gravity is coming from that somehow. And, so you have this spherical symmetry. That's essentially it. Now, the idea that it has to be from a point mass does not, that's not how it's implemented, right? This is what gravity will look like as a response to a configuration of mass which has got that spherical symmetry. It doesn't have to be at a point, right? So this sort of sets the frame for how we expect gravity to behave in general relativity with respect to more complicated situations. This is the backdrop, all right? This is the sort of blank canvas on which you can put other things. This solution will reproduce Newtonian gravity, among other things, all right? So there's a lot here to see. I would say most of which I won't really derive today, because to derive this fully is quite a monumental calculation. Starting with Carroll describes how to derive this metric from some general principles, and so he sketches how you can use spherical symmetry and some ideas about perpendicularity or orthogonality, if you will, in 4 dimensions to sort of build coordinates. And he explains how to build these coordinate systems on the expectation of the symmetry. And he works his way up to this from those principles. All right. So I'll show you some of that here, but I won't show you all of it. There's more in Carroll than I'm saying here, okay? With that said, let's go on. So this is the metric for a spherically symmetric gravitational field. So it describes the Earth or the Sun's gravitational field, and it is the unique spherically symmetric metric. So if you look at what happens, so this is some other things I should mention here right off the bat. If you put m equals to 0, you're back to the Minkowski metric, all right? Because this spherical term, this is spherical coordinates. So if you drop back to x, y, z coordinates, this will reproduce dx squared plus dy squared plus dz squared. So in fact, if you have mass 0, you're back to Minkowski space, which is what we would kind of expect, right? So general relativity, after all, is a natural extension of special relativity. And so let me just start telling you a little bit about his derivation here. All right, so here's a very sketchy sketch of his derivation. He says, basically, spherical symmetry brings us to this form. For some functions alpha and beta and gamma, it should look something kind of like this. And then he rescales R to, I think, to get rid of the gamma. So now he's down to alpha and beta, right? And as I was mentioning, he actually uses Birkhoff's theorem in section 5.2 to get to this form to start with. So he gives, that's what I was talking about, the orthogonality arguments and all that. He goes through some rather deep and beautiful ideas about how to construct coordinates in 4 dimensions from a symmetry principle to get to this form. But once he gets to this form, then the heuristic arguments, and well, I wouldn't say they're heuristic, but the I'm not sure what the right word is, but the arguments in section 5.1, I think it was, take over, and those are the ones I have here. So, like I said, we get to that, and then let's see here, page 2. So we've got this alpha and beta function. All right, alpha and beta function. Let's see here. Where was I? Here we go. So ds squared is minus e to the 2 alpha dt squared plus 2 beta dr squared plus the spherical part over here, right? And here alpha and beta are functions of r alone. So if you look at that, then you can identify the components of the metric for the time, radial, angle, other angle, and then we can derive, right? We can derive the let's see here. Let me just put this piece of paper away. We can derive the Christoffel symbols from the usual formula, right? The derivatives of the metric contracted against the inverse metric, and through, relatively straightforward calculations, you can get from here to here. All right. I did one of them just for kicks. So here it is, like to see the gamma RRR. To see the Christoffel symbol here, this one, I'm supposed to calculate these derivatives contracted against that inverse metric, but the inverse metric is diagonal, so like RR is the only one that's non-zero, having R there, so that forces me to put R here, which forces us to just have these 3 terms, but 2 of them cancel, and you're just left with the derivative with respect to RV to the 2 beta, which you can do, and it just collapses all the way down to the partial derivative of beta with respect to R. Of course, beta is just a function of R, so that's really just, beta prime, truth be told. So there's that. And then, let's see here, next, you can calculate the Riemann components of the Riemann tensor here, right? So, so remember the Riemann tensor we get from taking derivatives of the Christoffel symbols and then contracting the Christoffel symbols against themselves like this. And so using the formulas we said on page 2, you can derive, these are the components of the Riemann tensor. Like, for example, I didn't derive these actually, but you could, and that would be good homework for you to do, I think, because the homework at the end of this chapter is a little bit much. So a good exercise for a student in this course would be to pick a couple of these to see if you could work them out. It's kind of mundane, but it would be a good check on whether or not you understand the notation, what's going on here. And then next, you can calculate the Ricci tensor, and the Ricci tensor is found from contracting the Riemann tensor, like so, and these work out to these formulas right here. All right. For example, the phi one, so you contract the Riemann tensor like that with phi here and here. And so here there are actually 3 interesting non-trivial terms, because you could have TT or RR or phi or theta theta. You're not interested, the phi, like, remember it's anti-symmetric, so like if you put phi and phi here, I think it's 0. So these are the non-zero entries in the Riemann tensor. But when you put those over here like that, some kind of neat cancellations happen. Well, not cancellations, but you can group things together because there's a sine squared here, here, and here. Let's see here. Yeah. And so I factor the sine squared out, and you've got e to the minus 2 beta, and then you've got r times this derivative and that derivative. And then also this minus 1 is from that 1 becomes this minus 1 because I think there's a minus. So, oh, there's no minus. Why is that minus 1? Maybe it should be plus 1. Oh, that's that plus 1. Where's that minus 1 coming from? Goodness. Oh. Oh, that's the e to the minus beta. That's this term right here. So it's this e to the minus 2 beta gives us this minus 1. See, the e to the minus 2 beta is here and here. So this, and this give me these terms. And that one is from that one. Okay, anyway, exciting calculations aside, these are straightforward to calculate. If you wanted to sit and watch me do tensor calculus for the next hour, we could derive all these. It wouldn't be a big deal. You can do it too. All right, so we have this. And again, this all follows from that general symmetry argument. So then what? Well, let's see here. Then you can calculate the Ricci scalar. All right, so the Ricci scalar here, contracting the Ricci tensor across the metric, looks like this. And if you put in what these were from the last page, you get all this here. So this metric, what is it trying to do? It's trying to describe gravity in the vacuum around a spherically symmetric mass-energy distribution. Einstein's field equations give you that the Ricci scalar is 0. In fact, they give you that the Ricci tensor is 0. Right? So we actually have separately all these equations. These are all 0. And so if you set the things on the last page equal to 0, you get these equations. 0 equals to this plus that, which works out to this. But that means that the partial derivative with respect to r of alpha plus beta is a constant, which says that alpha and beta are just differing by, well, alpha is equal to minus beta plus a constant. So we can get rid of, I think we can get rid of beta at this point and just keep alpha, or vice versa. Let's see what we do. I think we just keep the alpha. He also points out that you can get rid of the c by rescaling the time coordinate to e to the minus c times t, and since that just amounts to rescaling the time coordinate, we might as well just put alpha equal to minus beta. And so then once you have that, you can go back to your battery's trying to roll all over the place here. You go back to the theta component of the Ricci tensor being 0, and that will give us that e to the 2 alpha is 1 plus, so you can just reverse, this is like a reverse product rule, I think. And then once you have that, you can integrate both sides, and then it gives you this, which gives you can solve for e to the 2 alpha being 1 plus c over r. And then what? All right, well then, all right, okay, then, all right, then he suggests that we use some rather peculiar labeling for the c, call it r sub s. That's going to be for Schwarzschild radius. But anyway, and then so we brought the metric into this form at this point. So it's starting to look like the metric I started with, right? It's getting closer to looking like this, right? You can kind of compare. It's almost the same. We just need to identify that the Schwarzschild radius is actually 2gm, and that's what we're going to do next here. How do you do that? Well, in the limit of the weak field limit, this should reduce to Newtonian gravity, right? So we worked that out in like the last lecture, I think. So let's see here. Oh, one other point of business is that this, if you put the metric in this form, it solves all the other constraints on the Ricci tensor being 0. So if we do this, we've already solved all the other equations. So it's, allegedly a general solution. And of the vacuum solution to Einstein's equations, okay, it's a general solution to that in this spherically symmetric case. And but we proved in the last chapter that the 0, 0 component of the metric is in fact 1 plus 2 times the Newtonian potential. And but that Newtonian potential is Gm over R. And so equating these two, we get that the Schwarzschild radius is 2Gm. And there it is. That's the Schwarzschild metric. And it's in the form in which it was found. All right. So what we're going to do for the rest of this talk is to look at how to understand what this means, some physical consequences of it, but then a more interesting mathematical question at the end in terms of so this is the metric on some space, right? And there's some weird things about this metric, right? Well, the biggest weird thing is that this is 0 when R is equal to 2Gm, right? And this is division by 0 when R is equal to 2Gm. So there's an apparent singularity at R equals, at the Schwarzschild radius, right? There's something funny going on there. But the question is, and maybe this is a hard thing to understand, is whether or not that's just an artifact of how we're approaching the problem right now, or that's a genuine feature of the geometry here. So let's start to get into that. But first, a definition: Rs equal to 2Gm is the Schwarzschild radius, and ds squared above is the Schwarzschild metric. All right. So what do I mean, genuine singularity? Well, there are singularities which are not really singularities because they're just coordinate defects. That's something that can happen. So let's look at an example of that. Like I just said, it's singular in the mathematical sense when R equals 2Gm. So in other words, these are not good coordinates. Definitely R, theta, phi, and t cease being a reasonable coordinate system when we're at the Schwarzschild radius, right? Certainly it's degenerate there. But is it just a coordinate effect? Now here's an example, probably the most mundane example of a coordinate effect that I could think of was the plane, right? Think about the xy plane. Think about polar coordinates, right? In polar coordinates, there's something funny going on at the origin, right? What's the angle at the origin? Well, you can't define the angle at the origin, right? The polar coordinates break down technically at the origin. So perhaps, right? Perhaps this is like that, and it turns out it is, but it's not at all obvious, and it takes, I don't know, the story that Carol tells, it takes about 6 different steps in order to get to a system of coordinates which makes manifest the fact that it's not a genuine singularity. So I think philosophically it's kind of a difficult problem mathematically to think about, because we're so used to, here's a set and here's an atlas, right? So we're coming at this manifold from a really different perspective, right? Like we've got a system of coordinates describing some manifold, yeah, we think, and then the question is, what's the rest of the manifold? I'll just say that we'll get to it, but let's think more about this. Is it a coordinate effect? Well, if it isn't a coordinate effect, if it's actually something genuine in the geometry, it should appear in the invariants of the geometry. Well, what are the invariants of the geometry? Invariants of the geometry, in other words, things that are not coordinate dependent, are scalars that you can form from the curvature tensor, for example. And so this isn't really proved explicitly in Carroll, I would say, but he makes some claims that essentially if you look at the invariance, there doesn't seem to be any invariant, which is singular at the Schwarzschild radius. So the fact that there isn't any singularity in the invariant objects that are derived from the metric goes to suggest that the Schwarzschild radius might not really be a geometric thing. It might be just a coordinate effect. What is geometric, though, is the singularity at 0. R equals to 0 is a genuine singularity because, as you can see from this contraction of the Riemann tensor, rather, we get this formula here, which is definitely not making sense at r equal to 0. Now, the Schwarzschild radius, or more specifically the surface defined by r equals 2 times g times m, this is known as the event horizon. And it does have physical significance. It's just not a singularity, as we'll describe. So a singularity would be a place where the math breaks down, all right? The math works just fine at the event horizon. It's just that the coordinate system we're working with is a local coordinate system. It doesn't extend past that. Yeah. So for example, just to give you a sense of what an event horizon would be, for the sun, so you have, let's see here, the radius, so what would the, let's see here, all right, let's see here. So I'm forgetting how to read my formulas here. I think what this is saying is that the actual observed radius of the sun is, roughly speaking, 10 to the 6th times g, mass of the sun. So on the other hand, the Schwarzschild radius is 2 gm naught, right? So the Schwarzschild radius is very much inside the sun. And the things we'll talk about happening at the event horizon, they're not actually going to happen inside the sun, we don't think, because this solution is for a vacuum, right? So the vacuum, there's no inside the sun, there's no vacuum, right? So the Schwarzschild solution, it would be something that you'd think about. You'd find the solution outside of the sun, all right? Outside of the sun is where the Schwarzschild solution would be. And then you'd have to solve a different set of equations which described the response of general relativity to matter inside the sun. And those two solutions would be glued together to form the full solution, something like that. Much like the situation if you take electrostatics, where if we have a solid charge that's smeared out, right, you have electric field that's, goes to its maximum value at the surface of the charge, and it linearly decays to 0 as you go inside. And then outside the charge, it decays according to the Coulomb law. So we kind of expect something similar here. Think of the analogy being that the Schwarzschild solution is analogous to the Coulomb law. It's like that kind of thing. All right, so let's go on. So their takeaway message here, there does not exist an event horizon inside the sun. The Schwarzschild breaks down inside the mass distributions. So, which is not to say that there aren't real event horizons for certain mass distributions. We'll talk about that. That's the situation with the black hole. All right, so you can talk about geodesics and orbits in Schwarzschild, and if you go back to the Christoffel symbols and put in what we've learned about alpha, here's the formulas for future reference. I don't think I'm really going to do much with them, but these are the Christoffel symbols for the Schwarzschild solution, and these are all in Carroll, of course. And these give you the geodesic equation, right? So you have 4 equations: time, radius, angle, and angle. These are the 4, nonlinear coupled partial differential equations. I know they're partial differential equations, but they're, well, I guess it's a system of nonlinear ODEs. It's not too bad. Wait a minute. Ooh. Well, they're bad. So I don't guess we know how to solve these directly, except in some special circumstances. But what we're able to do, and this is really kind of fascinating, is we're able to argue that if you do have a solution to this system of geodesic equations, and because we have the spherical symmetry to the problem, there have to be some conserved quantities. And in particular, there is a conserved quantity which we could call energy, and there are a conserved quantity which we could call angular momentum, defined as such. So the energy is 1 minus 2 gm over r times dt d lambda, where lambda is the parameter of the curve. It could be proper time, but this is the curves we're talking about. They could be space-like, they could be time-like, they could be null curves. All right, so lambda doesn't have to be proper time. It might be in a fine parameter or whatever. And the angular momentum is r squared d phi d lambda. All right, so these have to be conserved along the solution to this. So even though I can't solve these directly, these guys up here, I can't solve them directly, I can still say things about their solutions because we can study the conserved quantities of energy and angular momentum. In particular, you can also look at, I should mention, this is also something that's constant along a geodesic, right? So depending on whether you've got space-like, time-like, or null, you've got a null curve that makes this 0, and that is going to be, if you're along a null geodesics, then this thing is 0 along your curve. So more generally, you have this because you can put in what the Schwarzschild metrics are, components here, and from this you can derive that this is the energy squared, I think, and this gives me drd lambda. So he's going to like multiply by this factor, not the reciprocal, but multiply by the factor, kill the reciprocal. That leaves you just this. All right, and so you're multiplying by this, so here it is, and then you've got, this is L squared over R squared, I think, and then the epsilon brought to the other side. Anyway, it gives you this equation. And then if you tilt your head and squint, you can see that what you have is 1/2 drd lambda squared plus v of r equals to epsilon equals to e. And so v of r has the form of this. Now, if you've taken junior level classical mechanics, this will be reminiscent of when you studied the central force problem. And you'll recognize this as the effective potential for Newtonian gravity. But then there's an extra thing. This r cubed term is new. All right, so this is the effective potential. And again, it's very similar to Newtonian gravity except for the last term. And so then you can start asking questions like, okay, wait a minute, so what's a circular orbit? A circular orbit's going to be when the radius is going to happen. Let's see, we kind of expect circular orbits to happen at critical numbers for the potential. So if you look for those, differentiate this, set it equal to 0, you get this equation here. And if you think about it, if we put, so gamma is, what is gamma? Oh, gamma, you just tacked gamma onto this novel term. So he put gamma on the novel term, the term that's from that r cubed in the effective potential. All right, so he puts gamma there just as a kind of index. If gamma is equal to 1, you got gr. If gamma equals to 0, that drops you back to the effective potential that we, if we've had junior level classical mechanics, we've seen that discussed in there. All right, maybe not with exactly the same notation, but pretty close. Anyway, so some interesting comments, right? Like for gamma equals to 0, you can get the classical circular orbit predicted by Newtonian gravity, angular momentum squared divided by gm. And it's kind of funny interpreting this. He's like, well, if epsilon equal to 0, then that gives you infinity, right? And that's because photons aren't gravitationally bound in Newtonian gravity. And then he has a sentence, he has a paragraph where he kind of says, well, it's debatable, it kind of depends on how you approach it, blah, 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 whatever. On the other hand, if we have gamma equal to 1, then the effective potentials are approximately, for large r, pretty much the same. This is a sentence I didn't finish. The potentials are approximately equal. So like whether or not, if they think about R being large, then the difference between like general relativity and Newtonian mechanics in terms of the study of the relation of the potential energy on the radius for the spherical symmetric problem, they're really pretty much the same. I mean, because this is so tiny. However, when R goes to 0, this is the main event. This becomes, dominant. And so we expect really different behavior in general relativity for small radius in this problem. And so let's see here. And then for epsilon equal to 0 and gamma equal to 1, in other words, the relativistic case, you can get a circular orbit at 3 GM. So at 3 times 3 GM, you can get light to orbit this object in a circle. Light just goes round and around in a circle. But I think he says it's unstable, so if it gets perturbed a little bit, one way or the other, it'll fall in, might fall into the origin. And he has a page here where he describes that between 3 GM and 6 GM, there are unstable circular orbits which exist. When the radius is larger than 6 GM, you can get stable circular orbits. And he emphasizes that all of these comments are for geodesics, all right? So it's possible to do things. If you're not going along a geodesic, if you're just going along like a time-like curve, you can do other things. Like you can dip below 3 times GM and you can come back out. However, the more complete analysis that I haven't really shared yet shows that you cannot go, you can't take a time-like curve past this Schwarzschild radius and come back out. That you cannot do. And the reason you can't do that, the analysis there, it depends on the a study of the light cones and such. Let me see here. I think I wanted to show you guys a picture before I went on here. I forgot to make myself a note, but he has pictures of the effective potential for some different cases. So let me just show you, because I can't reproduce these. I'll find it eventually. Oh, here they are. So page 210. So here's what Newtonian gravity looks like for massless particles. I actually don't know. Okay, whatever that means. So here's the part I'm more familiar with. Newtonian gravity for massive particles, right? So you've got this, the 1 over r term dominates, so it becomes the potential energy goes up like that. In contrast, in general relativity, close to the origin, you have the negative r cubed term go down like that. So like once you get past a certain point, like you can't get back. Well, this is massless, but over here's the massive particles. But again, when you're close to 0, it's very, very, deep potential well. So there's that. Let's see here. Now, this picture is also useful. This is a picture of a precession, the precession of an ellipse. So, is that supposed to be the sun? I don't know. Maybe it looks like the Earth. I guess this is the precession of the moon, perhaps. So as the moon, it's probably still not right. Something orbiting the Earth, let's say. As it orbits the Earth in an ellipse, the ellipse, it kind of doesn't stay put, right? It kind of turns around like that, and that movement of the nearest point of the ellipse is called the precession. That's what we mean by precession of an ellipse. So I think that picture is helpful because I could say it in words, but I think that helps. That picture there. All right, so what are some experimental tests of general relativity? Well, here's some big ones. General relativity says that light should be deflected. It says that there's a particular precision of perihelia. Again, that's the point of closest approach of a planet to the sun. There are other para words for like the moon and other things. So he has the words in Carroll there. And then there's something called gravitational redshift. So let me just walk you through some of the calculations because I think they're interesting. I won't really do them. I'll just kind of show and tell them to you here. So the angular momentum was this, and so you can solve for that and square it. And then if you multiply the effective potential equation by this, you get to this. And then you make a substitution. And the thing that I think is interesting about this, if you're a physics student, is you've seen these things for classical mechanics. All this is done in classical mechanics for the central force problem, if you study orbital motion there. So you make this 1 over r substitution, and it changes this equation to this. And then you differentiate this with respect to phi and divide off the velocity term, and it gets you to the second order differential equation. And he points out that in the Newtonian calculation, this term is absent, but this was present. And then he introduces, he says, well, look at the Newtonian solution plus a perturbation, x1, and you plug it in there, you do a bunch of math, and enter the eccentricity. In the Newtonian case, you have 1 plus the eccentricity times cosine phi, where the eccentricity is 1 minus the semi-minor divided by the semi-major axis squared. And, well, long story short, what happens here is that he shows that the perturbation gets this as a solution. You end up with this 3g squared m squared over the eccentricity times the eccentricity divided by the angular momentum squared times phi sine phi. And then context puts the angular momentum squared to be equal to the eccentricity times the speed of light squared. Well, it puts it equal to this right here, okay? And there's also there's a GM that cancels as well. There's much more details in Carroll here, but I'm just trying to get to the main point, which is that you find that there's a precession of that angle, all right, equal to this. And so if you run the numbers here, the precession of Mercury is about 43 arc seconds per century, all right? And here, I'll read you the other details here because I didn't want to write them down because I'm lazy. So let's see here. He says, historically, the precession of Mercury was the first test of GR. It was known before Einstein invented general relativity that there was an apparent discrepancy in Mercury's orbit. So, in fact, this was, one of the crowning achievements of the 19th century's numerical methods. It took a long time to calculate this to the degree of precision to understand that there was an error. So we're talking about taking into account the perturbations of like the gravity of all the other planets to Mercury, and other things like, so let's see here. So the observed value of Mercury's precession was 5,601 arc seconds per century. However, much of that is due to the precession of equinoxes in our geocentric coordinate system, apparently 5,025 arc seconds per 100 years to be precise. And then he says the gravitational perturbations of other planets contribute an additional 532 arc seconds per 100 years, right? And that leaves 43 arc seconds per 100 years to be explained by GR, which it does. So, there's a lot to appreciate there in terms of like they had to not only calculate the contributions of Newtonian gravity from the other planets to Mercury, but also be be confident about the error in their calculations. Like they knew apparently 532 arc seconds per 100 years. And they were confident about that calculation well enough to know that there was a discrepancy of 43 arc seconds. So that was sitting there waiting to be explained by general relativity. That's not something Einstein had to go and find. It was a known problem. So that's one thing. All right, let me move along here. And then I didn't see anything directly about. I think I don't remember him saying anything, but I believe there was an expedition by Sir Arthur Eddington to look for the bending of light around a star or something. But I think there's some debate about that. I'm not sure if that's why Carroll doesn't have it in his book at the moment or what, but anyway. Gravitational redshift. So this is a pretty clean calculation. Certainly it's much easier than what I just skipped over there. So if you consider a stationary observer in this Schwarzschild scenario, the 4 velocity would have the spatial coordinate 0, and of course the contraction of the proper velocity, which should be -1. But then when you put that into practice here, that means that given the Schwarzschild coordinates, that you'd have proper velocity 1 over the square root of 1 minus 2gm over r. And if you had such an observer and they measured frequency omega of light along a null geodesic, then that frequency is given by this formula here. But the thing is, this just reduces to that because we have ui is equal to 0. And then, so this is equal to that. But remember that the energy is equal to this, so that's literally energy divided by the square root of 1 minus 2gm over r, all right? But then the thing is, but remember, energy is constant along the geodesics, right? So if energy is constant along the geodesics, then that means that omega has to change with r, because E can't change, right? So other things are constant along the null geodesic. G, M, E, all constant. The only thing that can change here is r. So that means omega must change as well. And so what that means then is that photons, if they're emitted at radius 1 and they're observed at radius 2, then the quotient of their frequencies is given by the square root of, as you can see there, 1 minus 2gm over r1 divided by 1 minus 2gm over r2. And if we're in the limit that r is much, much greater than the Schwarzschild radius, then you can apply the binomial series. And when you do that, you got this. Notice that there's a half power. The half cancels the 2. And there's a minus on the r1 and a plus on the r2 because this is the negative 1/2 power, which cancels the -2. That's why that's minus and plus. It's just binomial series. But anyway, so what this says is that the frequency goes down for r2 greater than r1, which is to say that there's redshift. On the flip side of things, if you have photons falling into a body, then they'd be blue shifted. I think it's pretty funny that they observed this at the Harvard Physics Building in 1960 over a 72-foot 72-foot range. So they were able to see the gravitational redshifting of photons over that short a distance. And of course, this is the thing that gets mentioned. They have to adjust for this to make like GPS and other things work correctly, because this actually is a significant enough effect to be it can't be ignored if you're working with a precise system these days. All right, so like it matters. You have to adjust for this. The frequency, if you emit a photon at one gravitational potential and you absorb it at a different one, then there's going to be a redshift as a consequence of that motion. All right. So finally, towards the end of the chapter, he starts coming back to the question of, well, why is it that the the Schwarzschild radius is just a coordinate effect, right? So there's a number of stages in this story. So I'll start with the first. So this we kind of derived this, not really, but I gave you some reasons for why this is true. All right, this is the Schwarzschild metric. And then this is the next thing that was done apparently is to introduce the so-called tortoise coordinate, and he has reasons for it. Okay, I'm not going to tell you the reasons, but he introduces this tortoise coordinate, and then that makes the metric look like this, which is, I mean, that's an improvement. At least there's not division by 0 at the Schwarzschild radius. Now it's just making this be 0. So, like the metric sort of drops to be two-dimensional at the Schwarzschild radius now. Okay, so I guess that's an improvement. And then, past the tortoise coordinates, the Eddington-Finkelstein coordinates enter in, and those are defined by shifting the tortoise coordinate and in time with a plus-minus transformation like this to introduce this u and v, and that gives you these coordinates. And I think these are actually such that I don't have this calculation here, but if you calculate the determinant of the metric, it's non-zero at the Schwarzschild radius. So these are actually non-degenerate coordinates at the Schwarzschild radius. So that's an improvement. And in fact, they allow you to go through the Schwarzschild radius with a future directed path in these coordinates, and you can follow a past directed path through the Schwarzschild radius with these coordinates if you want. These Eddington-Finkelstein coordinates. All right, and then next we introduce the. I don't even have a name for these. I don't think. He's like, well, the other thing you could do would be just instead of using v and r or u and r, you could just use u and v. And if you use u and v, this is what the metric looks like, where here r is implicitly defined by this lovely equation. And then you can define u prime and v prime like this. And if you do that, then the metric looks like this. And finally, we have come to a form for the metric where there really is no special significance to the the Schwarzschild radius. In this system of coordinates, the non-singular nature of the event horizon is finally manifest in these coordinates. And then past that, even better still, is the Kruskal coordinates. So Kruskal coordinates introduce this big T and this big R defined like so. In these coordinates, the form of the metric becomes very, very pretty. It just looks, it's much closer in some sense to being Minkowski. It's not exactly that, but minus dt squared plus r squared, and I mean it's just a very, very nice formula. And in particular, this is nice because it makes the null surfaces very, very. This system of coordinates just allows you to see everything. It's very, very neat. So let's look at it a little bit. So technically, those coordinates don't work for everything I'm saying here. Like, let's see how to say this. I think, to be fussy, those coordinates work for like maybe 2 sectors here. Let me just get on with it here. So this is the metric and the Kruskal coordinates, and t squared minus r squared is equal to this. So your coordinates t, r, theta, phi are the Kruskal coordinates. Here's the cool things. The radial null curves follow t is plus or minus r plus a constant. The event horizon in these coordinate system is just the lines t equals plus or minus r. So like the event horizon is this. And this is a TR diagram. I haven't put the. I hate to find. The thing is, I don't remember which way. I'm a 50-50. T. I hate to even draw it in. R, maybe. I think that's it. Look in Carol to be sure, of course. But yeah, so the event horizon is actually these two curves. Every point in this diagram is a sphere. because the you're suppressing the theta and phi coordinates, right? So like the unpictured part of the space-time are spheres. It's like every point corresponds to a sphere in some sense. And let's see here. Constant R surfaces are hyperbolas in the TR plane. Constant T surfaces are lines through the origin, where the hyperbolic tangent of that T over 4gm gives you the slope. And you might notice that as T goes to plus or minus infinity, this goes to plus or minus 1, which means you're back up to here. So the lines limit to the event horizon. And so to be fussy, I think this is the range for the Kruskal coordinates, and I think they actually only work for here. There are other Kruskal coordinates which are like a little bit different that would work for here, I think, maybe. I'm not 100% sure on all that, but this much I know, that essentially the story is this, is like we started over here, and then you can think about extending solutions past the event horizon a couple different ways. If you try to go past the event horizon by a future directed null ray, you can get into region 2, which corresponds to a black hole. This is, it's possible to physically traverse there from over here. On the other hand, if you look at past directed null rays, in other words, those are rays which had to start in 3 and go to 1. You can have that. That's what's known as a white hole. It's a time-reversed black hole. And then there's this asymptotically flat mirror of 1 over here on 4. And he mentions that people have thought about like forming wormholes between 1 and 4. That's kind of the only way you could get over to here. There's no time-like paths to get from here to here. You have to follow a space-like geodesic to get over there. Of course, those are hard to follow. So it's very interesting, like just the whole story of what the Schwarzschild solution allows for. I mean, these are in some sense extensions to the Schwarzschild solution. I think the situation is kind of similar to, oh man, I don't know what it's similar to, but this is just to me a very fascinating thing. There's a fellow who wrote a creation model based on the universe being a white hole and things. I don't think it's very popular or accepted much anymore, but people have tried to do interesting things with this. Let's see here. So I'm supposed to read some things from page 230 before I forget. Page 230. So he says, basically on page 230, he's describing how essentially the details of our universe and the way things happen mean that white holes are probably unphysical. How does he say it? What's the precise language he uses? He said, there's no need for a white hole, however, because the past of such a spacetime looks nothing like that of the full Schwarzschild solution. Okay, well, anyway. Well, you can read that page and see what you think of it. The other thing I wanted to mention briefly is, like, the current storyline on black holes, right? So, essentially, the question is, does every astronomical object keep shrinking until it becomes a black hole? And the answer is no. It depends on the mass. So, like, let's see here. Electrons are pushed so far together that they resist further compression simply on the basis of the Pauli exclusion principle. A stellar remnant supported by electron degeneracy pressure is called a white dwarf. Typical white dwarf is comparable in size to the Earth. Let's see here. White dwarfs are the end state for most stars. They're extremely common throughout the universe, he says. However, if the mass is sufficiently high, the star will reach the Chandrasekhar limit, where even the electron degeneracy pressure is not enough to resist the pull of gravity. Calculations put this Chandrasekhar limit about 1.4 solar masses. So I guess that would mean that our sun will allegedly become a white dwarf after it's done collapsing under gravity. So when that happens, it collapses down into what's called a neutron star, which is basically just a big nucleus, right? It's just neutrons and yeah. And these give pulsars. If neutron stars are like rapidly spinning, it gives you strong magnetic fields, and every so often you get these very energetic pulsars, which we have observed. And then past that, the neutron star mass limit is around 3 to 4 solar masses. This is called the Oppenheimer-Volkoff limit. And so it's believed that past that is a black hole. And but of course this is all speculative, right? Because if we knew more physics, maybe there would be some other kind of pressure to oppose it. But it does seem like there are black holes. And then there are these supermassive black holes, right? So like the story has changed a fair amount since I was in school. I would say that when I went to take an astrophysics class, like I think most people believed there was such a thing as a black hole, but there was still some kind of, have we really observed one, kind of like debating going on. And certainly there was debate about whether or not there had been an extrasolar planet observed. I think at this point everyone pretty much believes that we've observed extrasolar planets. And I think that from what I've heard and seen, there's a fair amount of consensus that, since that's what science is governed by, right, that we've seen black holes. Well, I don't think we've seen them, but we've seen evidence of them. Things that are so massive that there's really no other explanation except for a black hole. In particular, it's thought that there's a supermassive black hole at the center of most galaxies. Because you see things that are very large, moving very fast and in tight orbits, and the only thing to explain that kind of orbit is a very large mass. So it's interesting. In my lifetime, we've gone from black holes being kind of a curiosity to them being a necessary ingredient for understanding the large-scale motion of galaxies. But anyway. So that's what I have to say about chapter 5 in Sean Carroll's book, and there is much more to read there. I have just shown you the highlights here. But anyway, thanks guys.